oops, these are the variables that we're looking at in terms of data, and then we're trying to predict suspended sediment concentration using the other variables. So I can just very briefly summarize that each of us took a different model to like a different neural network to try and predict suspended sediment concentration. So I took MLP, Alexi took LSTM, Galena took Transformer, Bali took GRU, and we are going to compare the performance of these different models at predicting the suspended sediment concentration using this like very long data set. And does anyone have anything to add?
I think, yeah, for me. So one other thing we wanted to do is instead of basically just allowing the machine learning model to just learn on the data alone, we wanted to account for hydrological processes and how they impact our prediction. And that's why we're doing the GRU with some feature engineering so as to account for processes that could also impact the prediction, which just an LSTM or probably any other machine learning might not be able to capture.
Okay. Okay, great. So you incorporated some kind of hydrologic feature into the code, or?
So we're trying to inform the sequence length or the look back length
Yeah.
by looking at, I believe it was like the residence times or something. Ari,
Time
you
of
can probably talk about that
concentration.
more. Yeah.
Yes.
Yes,
And
I can briefly update on that.
Mm-hmm.
Yeah, so I tried to estimate time of concentration using the Cure pitch equation.
Yes.
I originally thought I could use there's a USGS tool called StreamStats. Maybe you've heard of it.
Yeah.
And I tried to use that, but our watershed is in an area that is not sort of available for StreamStats processing. So I wasn't able to delineate the watershed that way, which would have been the fastest way. I tried to do it in ArcGIS instead using USGS 10-meter elevation, like DEM, digital elevation model, but the processing is taking forever. Just for background, our watershed is like 56,000 square kilometers. It's huge. But it just happened to be the watershed that had the most data. So pretty much where we're at with that is I'm going to try and do a rough calculation using like a flow line of the major river in our basin. But also Moses found that there are some estimates online for this Sacramento River basin that we can use for time of concentration.
Okay. So the national hydrography data, which gives you the river length, you can download it GIS data. Most of those data, if you look at it, they have the hydraulic length in it. So the measure of hydraulic length, hopefully they have it for the California region. Then that gives you the hydraulic lengths that you need to incorporate into the model. Yeah, I mean,
Okay.
yeah.
Great.
So USGS StreamStat was not able to help. Oh.
Yeah, the whole Sacramento River, it says like bad upstream area, it's not a valid place to delineate a watershed apparently.
Okay.
Yeah,
You
strange.
Okay, so you delineated based on the USGS gauging station there?
Yes,
Where you
basically, yes. So I took the DEM and I used the USGS gauging station as like the outlet or the pour point
Yes.
in my analysis. Yes. So I was able to delineate the watershed boundary. I just wasn't able to get like the longest flow path and the slope. But I can actually do the slope now. So I think what you said, I can do that because I found the NHD flow line that you're talking about.
Yeah, hopefully they have it for that line. If you go to attribute table, then you can find it. There is a field there. They typically have it. Hopefully they have it for your study area. Okay, great job, guys.
Thank you.
Wonderful. So, yeah, I'm glad that you guys are implementing multiple kind of neural network model to see which one would be better fit to your data. And then great job with picking the study area where you have such a issue due to maybe kind of extensive urbanization, land use changes, regulations in the catchment. But great. So also you guys can also look into critical infrastructure in the catchment, see if there are any kind of gray infrastructure coming from reservoir or dams, going to wastewater facilities, all kind of things that can sediment deposition can impact those infrastructure, and then a consequence, it can impact the public and then community. So you can provide some kind of suggestions about the problem that you're addressing and why the importance of the research that you're doing and why it is important for community and public good. So great job, and I'm excited to see the result tomorrow. Hopefully you guys can you know, get a great result with the modeling that you're implementing, I'm sure. Yeah, well, I saw some of your comment about Optuna. Optuna is just right. It needs really huge kind of computational power in order to run it. But I'm glad to hear that you guys adopted Optuna and then also multiple neural network models. Good job. So anything
you.
else, any help or any kind of feedback you guys need at this time?
I keep running this weird issue when Collab doesn't allow me to use GPU.
Okay, let me check.
And I have only one session running and everything else is closed. But if I try to change a run type to GPU, it says, can it connect to GPU backend? You cannot currently connect due to usage limits in Collab.
Okay, can you
And
switch it to CPU and then, you know, open another Collab platform to run it? Sometimes, I mean, Collab doesn't allow you to open kind of, let me see. You know exactly what type of error you get?
yeah, well, it doesn't say the error number, but let me reproduce it. It is saying that it cannot connect to GPU due to backend issues. Well, basically that's the idea. I'll try to create a new notebook then. Maybe that will help.
Yeah.
I think I also read online that I think the usage limits for the GPUs are like dynamically determined per person.
Yeah,
just based
that's
on
what I
like, how much
figured.
traffic there is. Yeah. So I bet it's hard to actually know how much time you get on the GPU.
Yeah, maybe I was just in the wrong place in the wrong time.
Yeah. So yeah, that's the only computation you have on your laptop, right?
Yeah.
Yeah, maybe you reach the usage limit of it, and maybe you need to have like a cool down period of up to 8 hours.
Oh, okay.
4 hours in some case before GPU access is restored in your case. So maybe try again, or maybe you can have you guys, any of you used near Jupyter Hub. That is, I don't think you encounter any limit there.
Oh, okay. Yeah,
That's a
thank you.
Python platform, so you can use there too. And then Kaggle too, you know, I don't know you guys use Kaggle before, it's free as well. It's just gives provided similar notebook environment with free GPU access. So there also you can run your code.
Okay, that's a great
Try
suggestion.
Kaggle, let me give you some. Can use Kaggle kernels with GPU. So I send you a tutorial on this here. Send it in the chat. There's another platform like Colab. So you guys can use it. We used it before to run image processing models. It is really good. It's user friendly and provides free kind of computing resources. So yeah, feel free to use it as well. You need to create an account and then start running it. Okay, anything else you guys want to share? Okay, great. So let's move on to the next group, remote sensing group. If you guys are there, Nida, Ashish, Hassan, and Sanjeev. You guys are ready?
So we didn't really prepare the figures like before, but I'll try to share my screen from the notebook where we are running the code.
Okay.
I'm remotely accessing my computer. I'll try to do this. If I couldn't, I think Hashish is going to share his the the latest things that we after training the model, and I'll discuss it. But
Okay.
so I'll try to do this. Okay, you can see my screen.
Yes.
Okay, good. Okay, so I'll start from the beginning. Okay. Okay, so this is the study area. This is Arizona, and these are the pixels from GRACE that show the changes in terrestrial water storage. So what we are doing is that we are taking each pixel, the time series for each pixel, and we are training a model, an LSTM model for it, trying to train the model. And when we get a good result, we will use this model for the downscaling using all the predictors on a final resolution.
Great.
So this is the change of the average over over Arizona, and there is depletion in groundwater or terrestrial water storage in general, and this is what we are trying to see on a final resolution.
Great. So can you go to TWS plot again?
Yes. So this is just one date. So this is I think in 2022. So
Yeah.
this is just 1 month.
Oh, it's just for 1 month. Which
Yeah,
month?
this is not the trend or anything. This is just the values at 1 month.
Okay,
So it's
is it
like, yeah.
what month is it?
So here I'm doing it by the time slice 200. Yeah, so I think it's like, I don't 2022, because I have 256, I guess, time slices.
July. Yes.
Okay.
Oh, okay. Are you considering the water year or the beginning of the January?
The beginning of January.
Okay. Or that is great, but you guys know that in hydrology, we consider water year, right? When we run, I want to see, give you USGS report. You guys can look at it. So that you can set up your model based on that if I can find it. Water year. So this is the resources. It runs from October 1st to the end of September. So we call it water year. I am trying to find the national water kind of simulation that they do based on that. So that's how we do the simulation based on water year, we call it. So it doesn't go based on Gregorian and calendar year. So let me send this to you so that you can change the simulation run from October 1st, for example, October 1st, 2021 till September 30th, 2022. That's how it runs each year, okay? So if you want to run it yearly, okay, I don't know what this is. Okay. Yeah, so it has some information about that if you guys want to look into this. So we consider like a full water cycle if you want to run it. So what happening in the full water cycle with respect for total water storage, right? So
So
that's
because,
12 months.
okay, because all the predictors start at the same time and they end at the same time. And also we are taking full years. So even I know it's starting from January, but still taking full year. So would this make a difference in the prediction or in the training?
So when you want to discuss it from hydrology-related perspective or water science-related perspective, your run got to be based on water year. That means you will start your simulation run from October 1st till September 30th.
Okay.
Okay, so that's the timeline you guys got to consider it, not from January. And then explain what happened to water cycle during the water year prediction. So they call it water year prediction. So the prediction that we deal with in water resources, the timeline is from October 1st till September 30th. So even when we do any hydrologic model, large scale hydrologic model based on yearly data or even daily data, we got to start from October 1st to September 30th, unless you want to work on flooding issue, for example. You get flood, for example, in Texas, we got flood in July, first week of July, like few days. So you simulate that few days. So, but if you want to simulate like long-term, daily, monthly, yearly events, for example, from 2005 till 2020, then you got to set up your data based on water year. And that means you start from October 1st till September 30th.
Okay, but I think this will, the problem with this, I think we can try it, but it will take even, so we'll have less training data because it's gonna take 1 year out from the training data.
Okay.
But we can try it.
Yes. So then if you, for example, split it into different kind of segments, so you split it based on water year. So, okay, you say, I model it from October 1st till end of December. I got this result, or October 1st till end of November, I got this result. You mentioned in your report and in your presentation that your prediction follow water year based on USGS defined water year, so that you guys, you know, is meaningful when you simulate it.
Okay.
So not from January. So all of you, if you guys or running your model, make sure you run it based on water year. Okay, anything else?
Okay, so yes, so the predictors we are training, so we are trying to, so we have the NDVI, the land surface temperature, precipitation, surface runoff, subsurface runoff. This is modeled, also the AT and the soil moisture anomaly. And we tried variation. We tried to take the accumulation of these predictors also as inputs to the model to see if it's going to improve it. So the thing is with the accumulation is that it somehow retained the trend. And because GRACE is an accumulation of the change in interstellar water storage, it might add some knowledge there. So we were trying this also.
Yeah, nice. So one thing that you guys can do it is to add and drop those variables. Add them, run the model. Drop them, run the model, and see the performance. It's going to change it. It's going to improve it. If it improves, that means that variable influence your prediction.
Yes.
If not, that means it is insensitive.
So we tried feature importance or
Yeah.
permutation, yeah, so that we see which variables are contributing the most. But the thing is, for each pixel, because these are different models, we will have different contributing variables. So we took the most that might like improve the model for all the pixels.
Okay. Okay,
We're
great.
still trying with this. So we trained the model for 50 trials. So I'll give the latest result directly.
Okay, so that's the first initial kind of okay, your root
Okay,
mean
so this is here because the testing period was from, or the unseen data from 2019 until 2023. So what happens is that some pixels, the model is performing very well, and in others, it's not even learning very well. So for example, here you see the model is to some extent is good, but in the others, it's not. And when we change the predictors, for example, once we find some other pixels that are performing very well and others are not, even here, for example. So
Yeah.
we have a good result here, but here it's not learning or capturing the at all.
Okay, so your a little bit go up. Your first plot on the left, you see the second segment of your prediction, you have a lag, right? See that? So there is a delay in your predictions compared to your observation. So your prediction start with a delay, right? So
you mean here at this point, or
yes,
where?
you see that there is not much. The starting, you have a delay. The peak when it goes on 2022 01 or 02, that time scale. Actually, the start from 21.7, and then it gives you lag to the end. So you see how you can improve the lag. Can you give a lag to your data and then run it again and see whether it is going to help here? And then I would recommend you guys use Nash coefficient instead of root mean square error. It's just not very accurate for hydrologic related research. Use Nash coefficient and mean absolutely error, or MAE, as your objective function. And then see and compare your result. See which one gives you the best NSE, Nash coefficient, and the least mean absolutely error. So
Okay.
that too. And then you incorporated all those variables on the top that you presented?
No, this latest run, it wasn't with it was with all the variables without the accumulation of surface runoff and subsurface runoff. So I included the evaporation and the accumulated evaporation, and also the precipitation, accumulated precipitation, but not the runoff and subsurface runoff.
Oh, okay. Did you see any difference when you added those variables?
Um, for some pixels it improved, for others it didn't. So
Okay.
it's not consistent.
Yeah.
So it needs more trials, I guess.
Yeah. So you're provided 100 kind of runs, right?
Yeah, 50 trials.
Yeah. Can you improve that one as well? Do you have dropout kind of parameters there?
Yes.
How much you consider that?
So it's between 0.1 and I think 0.5. So it's trying different numbers.
Yeah. So try to reduce it and see how that's going to help, and then your learning rate as well, and improve the number of runs. Hopefully the model has enough kind of iteration to learn the pattern. See how that goes, and
Okay.
then change the objective function to Nash coefficient and mean absolutely error. And then once you're done, you can create your CDF, which stands for cumulative density function, and it gives you a visualization of which area of your simulation lacking is just in extreme values or in the average values. Your model lacking where you have better fit. So it gives you overall a good idea and visualizations of your simulation results. And then what else? That's it. Yeah, you have root mean square negative. So test it with Nash coefficient, and that's maybe you need to. Can you make a kind of different setup for each pixel and run it?
I'll try. So
Yeah.
I know we are short in time, but we will try to do it.
Yeah, because one setup maybe is not going to be the best kind of modeling kind of format for all this grids. Maybe you can see each grid, maybe it needs different setup to
Yes.
improve. Yeah,
Okay.
great job.
Thank you.
Yeah, wonderful. Okay. Any other question, your group? Remote sensing? You're good?
Yeah, we are good.
Okay.
Guys, you want to add something? I don't know. Ashish.
Oh, Tony, you're here?
Okay. Thank you.
Yeah. Yeah, thank you, Hassan. Great job. Already. Next is hydroback. Hydroback. Yes. You guys are ready?
Hello.
Hello.
All right, so just basically want to start off with the novelty of this, because I think we all come from different backgrounds, so we don't really know what everyone else is doing or why. So a few years ago, this theory of doing hydrology backward came about, and the theory behind that is to use stream flow to kind of inverse model precipitation, where generally we use precipitation to model stream flow. One of the novelties behind this is that we have a lot of gauges around the US, but also globally. And then we have a lot more areas that have no gauges. So we have no idea what the rainfall looks like, how that could lead to increase in stream flow, how that could lead to flooding. And so our idea was to use machine learning to help improve that precipitation estimation at the minute scale. And so we decided to go about this two ways. One way was to use an LSTM model with streamflow data that we have for 4 sites around the CONUS. So ideally, we would like to expand this to other regions, but for like a proof of concept, we just started with 4 areas in the US. One of them actually being a basin that Vidya looked at in one of her previous papers, so we could do that comparison. And we also decided to use a transformer model. So Maral will talk about this soon. But again, the intent of this was to see how these machine learning approaches could help us better predict precipitation at the minute scale. And so you guys might have seen an email yesterday about some techniques we were trying to use to kind of smooth out the data. So Maral will go into that for the transformer model that we tried to use. And what we've been working on today is just trying to get those data run through the LSTM and one specific case study for the transformer model. So Maral, again, will go along with her questions for the transformer. And tomorrow we'll talk more about the overall project. So it's a bit of a scramble right now, and I'm just going to pass the baton to Maral so she can talk about her awesome transformer model and our attempt at using that. So take it away, Maral.
Nice.
Okay, we right now we have only the data for one of those watersheds. So we have basically precipitation and discharge in 15-minute intervals, and we have also temperature, ET, snow cover, soil moisture, daytime and nighttime. For now, we are trying to get more parameters. You know that it take a lot of time. So this is our initial run. We used average moving for 7 records. This is the result, and we are underestimating. I sent you an email also. We were wondering how we could improve the model. And also I have some more questions that I don't know if we have time to ask. I mean, so
Sure. So this is your stream flow, right? Is it?
no, this is precipitation.
Oh,
So we use the parameters that I mentioned: discharge, temperature, ET, snow cover, soil moisture, daytime and nighttime, which are daily, but discharge is 15-minute to calculate 15-minute precipitation values.
oh, nice. So this is the validation result, right? Or this
This is
testing?
the test. This is the test.
Okay, so nice. So the precipitation gave you 80% agreement, which is based on your Nash coefficient. So can I look at your code? If you could share it with me, then there I can check it.
Give me a second. Could you see my screen right now?
Yes, I can see you.
So I used your basically code. I didn't do much of these things, but the only thing that I changed was the standards, how I standard the data. So
Precipitation is different, yes. Okay. So nice. So is that for LSTM? Oh, is it transformer, right?
yes, it is transformer, and I'm going to try to use up to now for
Yes.
uh
Use Optune, it should help you to improve it, hopefully, but it takes long time to run. Make sure you have enough kind of a space in your laptop. I mean, it runs on the browser if you use Colab, but anyway.
I'm using Nair.
Oh, you're using Nair. That's a wonderful.
Yeah, I
You
don't
don't get any kind of shortage of data, then that's wonderful. Okay. So yeah, Glena, you guys got to use Nair too, so you don't encounter any kind of computational issues. Okay, great. So I want to see it. It gives you go up a little bit so I can look at your push loss, the push train loss, the push train loss. You use PyTorch there, and then so you use early stopping then to you know, control the
Should I
fitting.
shouldn't
Uh-huh.
Shouldn't I use the earlier stuff?
Yes, you use it. It's
Yes, yes.
for fitting, okay?
Mhm.
So it's good. So how many runs you put it? I couldn't find it here. Maybe it's too small for me. The number of
If you have time, Vidya, we're also happy to meet with you after this so that we don't like take up any other groups
okay, that's
time,
fine.
so we can have
Fantastic.
another chat. But yeah, Morale's been great at kind of throwing herself into this and running this transformer. So appreciate
Yeah.
that.
Okay, then if you guys want to discuss it privately, that's fine with me. Okay. So
Is any other group using transformers? Sorry, I don't know. Who else
Yeah,
is.
we do kind of.
Okay, using it.
other pers-
Do you have the same issue? Or are you golden?
No, we have some issues.
Okay. Okay, we're in the same boat.
So you can't, guys, it's just this algorithm is very clever, but don't expect that you get 100% agreement between precipitation. You know, for precipitation simulation, you're getting 80%. That's really great. So precipitation is very chaotic, particularly in that area, upper Colorado,
Oh,
right?
this is in Maine, actually. I think you're using Maine?
Yes, yes, it is main.
Yeah. Okay, then have you guys consider like a snow component, a snow?
Yes, we have the snow coverage daily, I guess. Let me check again.
You put it as a learning kind of variable, right?
Yes, as input, correct.
Okay, good. So it provide additional learning to the algorithm to learn it. So, okay, great. So we can
It's-
discuss it privately if you guys like to,
Yes, sure.
but make sure you have the number of run for me. I'll look at that part of your code.
Sure, I'll do.
Yes, so make sure that your model hit the saturation so that your model learn, after that, that's the model performance is not going to increase, right? So that means it may meet when it meets the convergence. That means whatever you increase the number of run, you change the parameters, the performance doesn't improve. That means that's all you can get from your model. That's the optimization, optimized kind of performance that you can get from that model. So the max, for example, can get from that model once the model hit the saturation or conversion criteria. Okay. Okay, great. So you guys can stay. I can have a look on your stuff. Hydrovac group. And then the last group is drought forecasting. Assemble neural network for drought forecasting. Sophia, Jamie, Ethiopia, and Meg. You guys are ready?
Yeah. So we are especially interested in seeing how the drought develops and how this affects the decision at reservoirs. So in our work, we are trying to use the models such as LSTM, and still we are working on transformers to simulate the stream flow based on past weather events. From the simulations, we calculate the drought indicators like SSI, then which helps us to identify when and how the severe droughts are. So based on this, drought indices, we try to develop the reservoir operation strategies. This is like the overall idea. I can share my screen. So this is our study area, so which is the Upper Colorado Basin. And like we see here, we have been using the canvas catchments, it has got stream networks, the reservoir location. So the reservoir which we are interested in is the Taylor River Reservoir, Taylor Park Reservoir. And so what we are doing is we have considered 24 catchments in the Upper Colorado Basin.
Okay.
And we are running the LSTM model for all this. We are training all those 24 catchments using the LSTM model simultaneously. And
Yeah.
then we fine-tune the model to the Taylor Park Reservoir, to this outlet catchment. So,
Mhm.
so what we did was the data we considered was from 1980 to 2024, and we have stream flow as our target variable, and we have other features such as temperature, the precipitation. And also we have, these are considered dynamic attributes, and also we have a set of static attributes for each catchment.
Mhm.
Well, for the LSTM model from the initial runs, so we also actually did the Optuna hyperparameter tuning, but so I saved the folder in a drive in Google Colab. I didn't know it was temporary, so the
Yeah.
next day it
Use
didn't show
Nair.
up. So
Yes, use Nair. You guys are added to Nair resources. Based
yeah,
on
so yeah, we had
yeah. So that's nice. So what you done with those dynamic and static features?
so yeah, using neural hydrology's entity-aware LSTM model.
Oh, okay.
So yeah,
Yeah. Okay. So you
and
incorporated into your okay.
so we integrated their model, and we are trying to change the parameters and trying to see. Then we also integrated the Optuna and see what the hyperparameters are. So these are the results for the test period for like all the 24 basins. So we have RMSC, Pearson, NSC, MSC, and KG. We are still working on interpreting the results and modifying the parameters.
Yeah.
And so the catchment we are interested in to calculate the drought indices as this like a Taylor Park catchment. So this is how the simulated and observed stream flow looks for the test period.
Yeah. Okay. So
And
you know how much is the performance? Is it
the performance here is
overall?
overall it's doing good. Like so it's about correlation of 0.77, and when it comes to NSC, it is about 0.5, which is closer to 0.75.
Yeah, you have some kind of
There are also some catchments where the performance is very poor. So we had to
look,
figure out.
yeah, look into those catchments.
Mm-hmm.
You see if they are donor catchment, if they, release water to other catchment, and where they are standing in terms of the hydrological response. And then based on that, you can conclude that, why it is not improving if you try to improve it over time. So do you have your code? I looked at it if you want to share, or
I can.
yeah.
We'll explain this. Maybe we can have a private meeting to go through things.
Oh, yes.
Yeah.
Yes.
And maybe Ethiopia can explain the next steps, like how we calculate the drought indices and
Sure.
how we are planning to do the reservoir
Sure.
operation.
Okay.
Ethiopia, please go ahead. Yeah, thank you.
So using the predicted stream flow values for the 3-year period, we went ahead and calculated SSI, which is a standardized stream flow index. We used the entire time series to establish what a baseline period is so that we can classify drought severity based on extreme, severe, moderate, and mild conditions. For those 4 classes of drought severity, we integrated that with the baseline reservoir operation, which we derived from open access data sources. So for Taylor Park, we have that reservoir decision, which is a baseline decision rule constructed based on storage levels. So for a certain storage level, there is a predetermined reservoir release. So what we're doing is using the SSI values as additional inputs to the already existing storage-based reservoir release, we're going to assign weights based on what the SSI values indicate, and change what the reservoir release would look like. So for instance, if our SSI resulted in -2, indicating an extreme drought condition, that would be multiplied by an inflow weight, where the baseline decision to maybe release 100 cubic feet per second would be adjusted to something lower because we are facing a drought situation. So that's the final aim, which is looking at an adaptive reservoir simulation using the predicted, the LSTM predicted SSI, and then using that as input into our reservoir decision. That's the final goal.
Yeah, interesting. Okay, great. Very nice. Very nice. So you guys can stay, and then I will schedule who goes first to with Claudia group and Meryl Claudia group. So great. So let's see. You guys are good? You want to discuss anything else throughout group? Okay. So let me have a meeting with Claudia and her group. So Meg group, can you guys come back at 12:20? Use the same Zoom link. And then join the meeting at 12:20, okay? Make sure you be here 12:20 sharp. Okay? The rest, you guys go. Tony, would you like to stay and see how?
I can stay for a little bit.
Yes, yeah. Yeah, thank you guys. Have a great day.
Video.